2.3, functions. Okay, so as starting into functions, we're going to actually talk about relations. A relation is where you have two sets of data that relate to one another. I know, never use a word to define itself, but meaning that there's a piece of information in the first set of data, and that corresponds to a piece of information in the second set of data. Such as, if I were to take the list of all the names of the students in this course, I would have all the first names in the first list, I would have all the last names in the second list, and there would be a relation between them. In my case, the first name, Sean, would relate to the last name, Davis, in the second list. And that's what we're talking about. So it's basically bivariate data, meaning that there are two variables, or two inputs, and that they relate to one another. Or it can be one input leads to an output. But there's two pieces of information that are tied together, such as heights and weights. A very common thing to get someone's height and get their weight. So we could have a list of heights and the associated weights. They mean something tied together. They don't mean quite as much when separated. So with a relation, there are a number of ways that you can show relations. I'm just going to show them as ordered pairs. We're familiar with that. So I could have the relation 3, 7, 2, negative 5, 8, negative 2, 5, 7, 6, 1. And this is a relation. I have an input, I have an output. I have an input, I have an output. An input, an output. An input, an output. An input, an output. Okay, so this is a relation. Let me just add one more in here just to make it a little more exciting. Three, 4. So now we have 1, 2, 3, 4, 5, 6. 6 ordered pairs or sets of data in this relation. 3 relates to 7, 2 relates to negative 5, 8 relates to negative 2, 5 relates to 7, 6 relates to 1, and 3 relates to 4. Now I could actually show this relationship visually by doing something like this. I could put my x values or my inputs in here, and I can just say I've got a 2, 3, 5, 6, and 8. Those are all my inputs. And then I can put my outputs in another bubble. And let's see, we have negative 5, negative 2, 1, 4, and 7. I think that's all of them, right? So that's all my outputs. Now how I can show this relation is I can draw arrows from each starting point to its ending point. So I've got 3, 7, so 3 goes to 7. 2 to negative 5, 2 to negative 5. 8 to negative 2, 5 to 7, 6 to 1, 3 to 4. And that demonstrates visually my relation. I've got a whole bunch of inputs, a bunch of outputs, and they all tie to each other. Each input ties to an output. So that's a relation. Well, what's the difference between a relation and a function? The difference between a relation and a function is that in a relation, any input can tie to any output. But in a function, for each input, there can only be one output. So for each input, there can only be one output. But there can be numerous inputs that go to the same output. So looking at this relation, I want to determine whether it's a function. And I see that the 2 goes to -5, so it only goes one place. I see that 3 goes to 4 and to 7. Therefore, this is not a function, because if you tell me that you inputted a 3 into this, I can't tell you what the output is. I can tell you it's 4 or a 7, but I can't say for 100% surety that it's which one of those it is. So that's the difference of a function. This was a relation. 3 gave you 4, or 3 gives you 7. But in a function, you can't have this duplication here. You can't have 3 sending you 2 different directions. 5 gives you a 7, 6 gives you a 1, 8 gives you a -2. So what really made this a relation but not a function? It's this last one here that I added on. You remember I kind of added that one on at the end and said, let's put that one in there. Well, that one is what caused the problem. Without that, and I don't even use that 4 anymore, right? This is a function. It's a function because you tell me that the input's 2, I know the output's -5. You tell me the input's 3, I know it's 7. You tell me the input's 5, I know it's 7. You tell me the input's 6, I know it's 1. You tell me the input's 8, I know it's -2. Now you may be looking at that and go, well, wait a second, Mr. Davis. There's 2 of these inputs going to that 7. Doesn't that not make it a function? And the answer is no, that does not make it a function. Functions can only have one possible output per input. You could have all of the inputs going to the same output and it would still be a function. If you had the function y equal to 4, right? Y equal to 4 says no matter what x value you have, y is going to be equal to 4. And that is a function. That's a horizontal line, which is a function. So it doesn't matter how many times you get the same output. What matters is any given input can only have one possible output. But any output can have a number of inputs related to it. So that's the difference between a relation and a function. Relation, they're just related to each other. A function, each input has to have a definite output. You have to be able to look at it and say, if you give me this input, I know exactly what the output's going to be. There's no, it could be this or it could be that. So ordered pairs is one way that we can give a function. Another way we could give a function is by using a table. So now we have first of all, we know it's a relation. Question is it a function? Because it's a relation just because it has x and y, and each thing has its associated x or y value. Is it a function? Well, do we have any duplicate x values? 21, 36, 42, 18, 22. So no, we don't have any duplicate x values. So with that, there's no way that we're going to have an x value go to more than one possible output value. So yes, this is a function. It's also possible if we had a duplicate, we may have 21, 16, just to grab something easy here. So I do have a duplicate here, but it still puts me to the same output. So that's okay, that's still a function, because if you tell me the input's 21, I can tell you the output's 16, because either time we had 21, we had 16. So that is perfectly allowable. So that's another way that we can give a function. We can also give a function by using what we call a rule. A rule is simply an algebraic relationship. Y is equal to 3x minus 2. That is a rule. It says take your input, multiply it by 3, and subtract 2, and that is going to give you your output y. And this is a function because if you recognize that that's y equal mx plus b, it's the equation for a line, and it's not a vertical line, right? So it is, so if you look at any line, for each input, there's only going to be one output because it doesn't bend or curve. So as long as, so any input will give you a different output. So lines, unless they're vertical lines, are functions. So that's a third way that we can get a function. We can get it by ordered pairs, we can get it by a table, we can get it from a rule. All those things can come together to go as a function. And remember, the difference between a relation and a function is that a relation just relates or ties together an input and an output, or a set of inputs with a set of outputs. Whereas a function, for each input, there can only be one possible output. So there you go. So that gives us that. Let me take a quick look over here. Okay. What I also want to cover with that is domain and range. Well, you know what domain and range are, right? It's that the domain is the list of all possible input values. The range is the list of all possible output values. And I shouldn't really say list. I should say the domain is all possible or allowable input values, and the range is all possible or allowable output values. So it doesn't necessarily have to be a list. It could be an inequality. It could be everything. In fact, what we will assume for this course is that unless otherwise specified, or unless we see that there's a reason otherwise, that the domain for our functions is all real numbers. We're going to stay within real numbers. And the assumption is that in general, that means that the range will also be real numbers, except things that preclude that possibility. Well, what could preclude that possibility? Well, first let's look at a couple relations and see what we're talking about. If we have y equal to negative 2x plus 5. Well, that's a line. It has a slope of negative 2, so it looks a little bit like this. Okay. I didn't put the grids up and everything. It's just showing slope is negative 2. It's a line that's slanted down. And so we have this line. Well, what's the domain and range? Well, technically, this is a line, right? So there should be arrows on both ends. The domain for this function is all real numbers, from negative infinity to positive infinity. We can take any x value and plug it into this, and we'll get a y value out. In fact, if we were to plug in all possible x values, we would get all possible y values, meaning that the range of this function will also be from negative infinity to positive infinity. So basically, this goes to the left forever, it goes to the right forever, the domain, it goes up up forever, and it goes down forever, the range. Because remember, if you're talking about a coordinate axis, that's x, that's y. Right? So the domain is all possible x values, the range is all possible y values, or the outputs. And a line, the domain and range are both all real numbers or from negative infinity to positive infinity. So not too bad with a line. Well, what if we have y is equal to x squared minus 3? And we'll get into this further in a few more sections. But if we have this, I'm going to give you a basic drawing of this. It looks something like this. It's a parabola that's been shifted down by 3. So there's 3 right there, negative 3. So what is the domain and what is the range of this? Well, it goes on forever to the right and to the left. So the domain is from negative infinity to positive infinity. Remember, you never include infinities. They're always exclusive since it's just a concept. And the range starts at negative 3, right? There's no value below negative 3. So it starts at negative 3 and goes up forever to infinity. So it's negative 3 inclusive because it starts at negative 3 and includes negative 3, up to infinity. Infinity is not included because it's just a concept, not a real number. So that's how we can get the domain and the range. What if we have slightly different function? Y is equal to x plus 2 over 3x minus 1. Well, here, the domain is what? Well, we can't allow the denominator to be equal to 0. So we have to look at 3x minus 1 equal to 0, 3x equal to 1, x equal to 1, 3. So basically the domain of this is all real numbers such that x is not equal to 1/3. Because 3 times 1/3 gives us 1, 1 minus 1 is 0, and then we got to divide by 0. So we can't allow that to happen. What about the range of this? Well, that gets a little more complicated. Because we're looking, well, what's the range of this? Well, how high is it going to go? Or how low is it going to go? What can't the value be? Well, I can try that once. I could graph it. So I could graph it and see what happens. I could plug it into a graphing calculator or some device and have it plot it for me, and then that'll give it to me, right? I can look and see where it's limiting, because basically what's going to happen here? Well, this is going to approach 0, but never reach 0, right? So if this is approaching 0 and never reaches 0, then anything above that should approach either negative infinity or positive infinity. So basically, as this approaches negative 3, then this is going to, negative 1/3, this is going to approach 0, and 1/3 plus 2 gives us 2 1/3. So 2 1/3 over 0. So that's 2 1/3 over extremely close to 0. We can't say over 0, right? It's going to give us an infinite value. So if we have just larger than 1/3, then this is going to be a positive value, so it's going to basically approach positive infinity. If we have this as something just slightly less than 1/3, then this is going to be slightly negative, so we're going to approach negative infinity. So the problem is, what happens in between? Where is there a value? What is the limit there? What's going on there? So we know that it's going to go to negative infinity, and we know it's going to go to positive infinity. Well, we've got to assume that something's going to happen in the middle there, because at some point it can't do what it's supposed to do. So I guess we can look and see, well, what happens if we go to infinity? Well, if we go to infinity for our input, then we're going to get infinity over infinity, which is essentially 1. So do we have anything that's going to block this? I don't know, it's hard to tell at this point. That's where the graphing comes in. Will we actually come up with some output that's not possible? You would think that as you approach this, but that's going to be your discontinuity, where you're negative infinity, positive infinity. So can I end up, is there somewhere that it crosses over? I don't know. We do know that it's going to reach negative infinity, it's going to reach positive infinity. The question is, I should put a little u in there, right, for union. The question is there some discontinuity there? You would think that there would be, because if you can't allow the domain equal to 1/3, then you'd think there would be something that relates to that. And you can go and plug that into your graphing calculator, or go onto Desmos.com or any other graphing utility and graph this and see what you find. Is there a discontinuity in the range or not? So I'm going to leave that to you. But it was fun to look at it and kind of get an idea with it. But we can go through and we can determine domain and range from something like that, or we can even look at the graph of a function. Maybe I have a function I'm just going to number these. You remember, always number your axes. I'll be good and put my little arrows on the ends, right? So maybe we have a function that looks like this. So I have a function that looks like this, and just to make it a little clearer what we're seeing here, just going to put a dotted line there. So what is the domain and range of this function? Well, the domain is the list or all possible inputs, and we see that at x equal to 1, we have a discontinuity here. We have an asymptote. This is getting closer and closer to x equal to 1, but it's never actually touching it. And this is getting closer and closer, but it's never actually touching it. So we know that the domain is all real numbers except for when x is equal to 1, so x not equal to 1. And what about the range? Well, the range, we see that the x-axis is acting as an asymptote, so y can't be equal to 0. So domain and range taken off of a graph. So when you're given a graph, it's actually one of the easiest things to do, because you look and say, okay, well, where is it not going? We can simply look at that. It's kind of like when we did the domain and range off of the parabola there. it was pretty straightforward. All real numbers for the domain, but for the range, it was from -3 inclusive to infinity. So finding a domain and a range. Okay, associated with this, and I'm going to put another graph up here. Remember what the difference is between a relation and a function, right? A relation just says this input corresponds to that output. And it doesn't matter whether there's duplication on either side. Whereas a function says that for each input, there's only one possible output. Well, if you're looking at things graphically, then we can look at something like that, and we ask, well, is this a function or not? And we can look at it and say, well, with what's going on here, each x value only gives you one possible y value, so therefore this is a function. Well, visually we can look at it and say, if I were to draw a vertical line anywhere on this curve, so crossing anywhere, it would only cross the curve at one point. So I come here, I draw a vertical line, it only crosses through the curve at one point. I come over here, I draw a vertical line, it only crosses through the curve at one point, through the curve at one point, through the curve at one point. This is called the vertical line test. So the vertical line test simply says that a relation is a function if there is no place on that relation that you can draw a vertical line that touches the relation in more than one point. So basically, you can draw a vertical line anywhere you want on this graph, and it only crosses it once. That's the vertical line test, and therefore it passes the vertical line test. Whereas if I drew something like this, and said, is this a function? It's obviously a relation. Every point on here can be defined by an ordered pair. But is it a function? No. I can draw a vertical line and have it pass through that curve in more than in one point. Therefore, this is not a function. What about now? Is it a function? Yes, it's an interesting looking function, but it is a function because now anywhere I go, I am never going to pass through the curve more than once if I draw a vertical line. You actually have this gap here. So there's some values that cannot be part of the input, right? Part of the domain. But this is a function because there is no place that I can draw a vertical line and have it touch it more than once. So that's the vertical line test. It helps us to determine if we have the graph of it, whether we have a function or not. Okay? Just looking at the additional stuff we want to cover here. So variations in a function, I'm just going to read some definitions to you. I'm not going to write them on the board. But a function is a relation in which each distinct value of the first component of the ordered pair, there is exactly one value of the second component. So it's a function is a relation in which for each distinct value of the first component of the ordered pair, there is exactly one value of the second component. A function is a set of ordered pairs in which a first component is repeated. for which no first component, I'm like, that doesn't sound right, for which no component is repeated. Never try to read Mr. Davis's handwriting. And a function is a rule or correspondence that assigns exactly one range value to each distinct domain value. So for each input, there's exactly one output. So now I want to mention function notation. What we've done right now, we said y is equal to 3x minus 7. Now, we said this is a line, this is a function. Right? Function notation, basically, instead of putting a y here for the output, we say y is actually a function of x, meaning that you put something in for x, you get a value for y. So y is a function of x. Change the x value, you get a different y value. So we write that as f of x, or function of x. So we're saying that the output is a function of x. It is equal to 3x minus 7. It's just another way of saying y, the output. F of x, this function of x, is 3x minus 7, means change x, the output changes. So that's function notation, nothing fancy. You just turn y into f of x. Or if we have a different variable, you turn the output into a function of that different variable. And many times we do use f of x, but there's nothing that says that we can't use other variables. So you'll see g of x is equal to 4x squared. G of x. It's still a function of x. G is a function of x. That's really what it's saying. We think of this as f of x, function of x, but it's actually the function, it's actually f is a function of x. G is a function of x. So we're basically saying, now calling f the output with that particular input. Well, one of the cool things once we change and go into this notation is we can now state what we want that input to be and find the output. So I've got these two things here. I can say f of 2. F of 2. What that says is replace x in the function f of x with 2. So it says, say, 3 times 2 plus 7. 3 times 2 is 6, plus 7 is 13. So f of 2 is 13. G of negative 1 says put negative 1 in place of x. 4 times negative 1 squared. Negative 1 times negative 1, or negative 1 squared, is 1. 1 times 4 is 4. 4. Function notation allows us to do this. So this is pretty cool because now we can not only define this relationship as a function, but we can even plug in values and say, okay, f of x is 3x minus 7, find f of negative 6. And you plug negative 6 into here, so 3 times negative 6 is negative 18, minus 7, negative 25. So f of negative 6 is negative 25. And it's that simple. Just plugging that in there. So there's really no difference between f of x is equal to 3x minus 7 and y is equal to 3x minus 7. But these do allow us to, 1, tell you certain values to plug into it to get an output. And 2, they allow you to relate to this numerous times, because now I can say, if f of x is this, now work on it doing such a thing. Take that function and add it to this function. Take this function and divide it by this function. Take this function and plug in a value for x. So it gives us a much better way to relate to these functions. Pun only slightly intended in that. So dealing with our functions and function notation, which is pretty cool. Now what we can also do, and I know I'm slightly off here, is actually, I'll pull this back in again. So let's say we have a function, so we're just going to give you a function, and this one's pretty straightforward. Y is equal to x squared plus 2x minus 3, and I tell you to put that into function notation. Remember, the only difference for function notation is we just go f of x is equal to x squared plus 2x minus 3. So that's not so bad. There we go, function notation. Now that I have function notation, I can say, well, f of negative 5 is equal to what? Negative 5 squared, remember we're plugging in negative 5 for each of the x's. That's all it's telling us. Plus 2 times negative 5. Trying to make that 5 actually look like a 5. There we go. 2 times negative 5. I see on the screen that that's not very visible, so I'm just going to erase it and put it back in there. There we go. That's more legible. And then minus 3. Negative 5 squared is 25. 2 times negative 5 is negative 10, minus 10. Minus 3. So we have 25 minus 13, or 12. There you go. Now another thing that we can do with this is we don't have to necessarily just plug in a numerical value. We could plug in another function or another algebraic expression. F of x minus 3. Well, what does that tell us to do? Well, that says take anywhere there's an x in here and fill in x minus 3. X minus 3 squared plus 2 times x minus 3 minus 3. Now we may leave it like that, but we probably want to simplify it somewhat. Remember, x minus 3, that's a special, or I should say x minus 3 squared, that's the square of a difference, which can be done as x squared, can be, and if I have the square of x minus y, it's x squared minus 2xy plus y squared. So I can square the first term, x squared, double the product of these, so minus 6x, square the last term, plus 9, distribute 2 through the x minus 3, and that gives you 2x minus 6, plus 2x minus 6, minus 3. And now I can combine like terms, and I get f of x minus 3 is equal to x squared. I've got minus 6x plus 2x gives you minus 4x. And then I've got plus 9 minus 6 minus 3. 9 minus 6 minus 3 is 0. So f of x minus 3 is x squared minus 4x. So we can do a lot of nifty things with this. Yes, I used the word nifty. Okay? But there's a lot of things we can do with this. It's a very powerful capability to treat things as a function and write them in function notation. You can do a lot of combining things together and a lot of algebraic manipulation using that. Okay. Increasing, decreasing, and constant functions. Now we're going to start with them actually as the functions being such, and then we're going to break them up into pieces. So increasing, so an increasing function is a function that as x increases, or as the input increases, the output also increases. So as x goes up, y also goes up. And obviously that would mean the opposite of that, as x goes down, y goes down. When we look at it as x increases, y increases, if that's the case, you have an increasing function. And we should say for all points on the function. A decreasing function, as x increases, y decreases for all points on the function. So as x continues to get larger, y gets smaller. It decreases. A constant function, as x increases, y remains the same. It doesn't go up, it doesn't go down, it just remains the same. So therefore y is constant no matter what x are. Now if you remember, I showed that as an example and said, well, if you have y equal to, I can't remember if I said 4 or 5, but if you have y equal to 4, that's a horizontal line. Well, that's a constant function. No matter what input x you put into it, you're always going to get the same output, y equal to 4. So that's a constant function. So we can look and say, well, if I have the following graph, is it an increasing function, a decreasing function, or a constant function? Well, as x increases, so does y. Therefore, we have an increasing function. As x increases, y remains the same. Constant function. And we'll see if you can figure this one out. No, you can't answer before I've even drawn it. And we have a decreasing function, right? As x increases, y decreases. It has a downward trend. So a decreasing function. Well, that's good. And there are certain functions that are always increasing, and certain functions that are always decreasing, and other functions that are always constant. But more often than not, you run into functions that are a mixture of these. They're increasing, decreasing, and constant at certain times throughout the function. Again, always got to label these. Always make sure you label it correctly too. It's always a little amusing when you see something, someone labels it and they put this as being -2 and then that as -4 and you're going, not really. Alright, so we've got our grid. Okay, so I have this function. Well, I have a relation. Is it a function? Passes the vertical line test, right? No matter where I look, if I draw a vertical line, it only passes through this relation once. So therefore, yes, it is a function. It's not a smooth function. It kind of goes up here and then jumps down and goes there. It jumps, it doesn't flow smoothly, but it is a function. So now I want to know over what intervals is this function increasing, decreasing, or constant. So I'm going to put increasing, INC, decreasing, DEC, and constant, CONST. So I see here that And don't let the arrows confuse you. As x increases, so as we move from the left side of the function to the right side of the function, what is happening with y? Well, I start here, and you see this arrow says it's going on forever. So we are basically starting at negative infinity for x. And this is going down, so we're actually starting at negative infinity for y also. And as we go to the right, as x values increase, so do our y values. So we're increasing from negative infinity to here, which happens to be at x equal to negative 2. And that negative 2 is included, that is a point there. So it is increasing from negative infinity to negative 2, inclusive. We always use the x values when we're giving these intervals. To be really honest, I don't really care what the actual y value is at the endpoints of it being increasing, decreasing, or whatever. I care about at what x values, what interval of x, is it increasing, decreasing, or constant. So then from negative 2 going over, as x increases, we see that it's falling. So it's decreasing from negative 2. And remember, it includes that negative 2. And it's this negative 2, not that negative 2, this one. A little confusing there since they're both negative 2. But we'll see it a little better here. As we go down, it decreases until x equal to 1. Not y equal to negative 5, that's now we're looking at x equal to 1. And it includes that, so 1. So it's decreasing from negative 2 to 1. Then from 1 to until 3, it is constant. As x increases, y remains the same. So it is constant from 1 to 3. And then at 3 it starts going up again, so it is increasing from 3 inclusive to positive infinity. So this graph is increasing from negative infinity to negative 2 inclusive, and from 3 inclusive to infinity. It's decreasing from negative 2 to negative 1 inclusive, and constant from 1 to 3 inclusive. And that's how we look at a function to determine where it's increasing, decreasing, and constant. One thing I want to point out to you and make clear, it is not constant at that point. It is increasing up to that point, and it is decreasing beyond that point. But it is not constant at that point. That point is instantaneous. So it's not holding at, that would be like you have your car accelerating, and then while it's still accelerating, so let's say you use cruise control, because that'll allow you to do it. You're using cruise control, and you set cruise control for a high value, and you slow down, and then you hit the resume button so that it'll accelerate up to the original speed you're at. While it's accelerating, you slam on the brakes. Slamming on the brakes suddenly causes your car to decelerate quickly. It did not hold a constant speed for any time. What it did was it was increasing, and then it went directly to decreasing. So you don't have a constant at this change. Be very careful about that. I wouldn't have thought to mention that, except I see people make that mistake. They tell me that this is constant, and it is not. It is increasing to that point, it is decreasing from that point. This is constant. When it maintains a value for a period of time, then it is constant. Another example I want to show you with this, because this is where people are even more likely to make that mistake, is something like this. This is a very poorly drawn derivative of the function f of x is equal to x cubed. Very poorly drawn, saying that this is wider than that, even though it should be symmetric with respect to the origin. So, but what throws people off here is they see this go up and then go across and go up, and they look at this middle point here and they go, oh, it's constant there. No, it's not. This is always increasing. It increases from negative infinity to positive infinity as x moves from negative infinity to positive infinity. So it's always increasing. So just be aware of that. Also, you would write this as increasing from negative infinity to positive infinity. The second mistake that I see people make with this is they'll say it's increasing from negative infinity to 0 and from 0 to positive infinity. I see people do that because they go, oh, it's increasing up to here and then it's increasing again. That is not correct. It's not increasing and then commencing to increase again. It is constantly increasing or continuously increasing. So keep those things in mind. Just common mistakes that I see that we should know better than to make those mistakes. And that finishes all that we need to cover for section 2.3 functions.